Now we have the definition of a concept called orbit at this point. Let the group G act on set A based on the definition we have given earlier. For an element X in set A, the set defined in this way is called the orbit of the element X. So let's look at what this set is. Gx, this is how we denote it. And the set of elements in the form of Gx, where this small g is a permutation in set G. Okay, so simply put, this is the set of elements that you can obtain by applying all the permutations in group G to element X. Okay, so this is the set of all elements you can obtain by permuting element X. That is simply what this is. Now, the set of all orbits is denoted by this here, division G, and it's possible to prove that this forms a partition of set A. Okay, so an element X in set A is said to be fixed by, or is said to be an invariant of G, some permutation in the group, if the permutations, all of, this particular permutation G maps the element X to itself. Okay, so it's called an invariant of the permutation G if the element X is mapped to itself. And again, we define this set A to G as the set of elements in set A that are mapped to itself through permutation G. Okay, the set of all elements in A that are fixed by the permutation G. Now at this point we are ready to give Burnside's lemma, and the statement is the number of orbits is equal to the average number of points fixed by an element of G, group G. So this is the formal statement. And this, I'm sure, all looks a little bit confusing, maybe vague, and maybe it's not obvious what it means. So let's do an example. If you recall the example I gave when we discussed groups, this is the symmetry group of a triangle. And here we have 6 elements in the group, namely the identity permutation. Okay, 1 is mapped to itself, 2 is mapped to itself, 3 is mapped to itself. Number 2, we have 1 rotation. So here, 1 is mapped to 2. So this is this rotation. 2 is mapped to 3, and 3 is mapped to 1. So what this is if you rotate this triangle in this direction once, or maybe you can call this 120 degrees, depending on your approach, you obtain, well, if you rotate that actually, 1 becomes here, 2 goes here, and 3 goes here. Okay, so this is the picture you obtain when you apply this permutation to this triangle. And we have the double rotation where you rotate this triangle twice, again in this direction. So 1 was here, but then goes here and then comes here. So 1 ends up here, and 2 goes here, and 3 goes here. Okay, so as you see, 1 goes to 3, 2 goes to 1, and 3 goes to 2. And it's good to write also these in cycle notation. And you see in this 1, 2, and 3, they all go to themselves. So we have 3 cycles of length 1. In the rotation, we have 1, 2, 2, 3, 3, 1, and so this is a single cycle consisting of 1, 2, 3. And R square which means a rotation either twice in this direction, or maybe you can look at this a single rotation in the other way. That's also valid. And you see the cycle here is 1, 3, and then 3, 2, and 2. So this is 1, 3, 2 cycle, a single cycle of length 3. And we also have the flips. So a flip across this axis. So let me apply this flip here. So 1 stays at its position, and 2 becomes 3, and 3 becomes 2. Okay, so 1 stays at its position, 2 goes to 3, and 3 goes to 2. You see I have one cycle here, 2, 3, then 3 to 2. So this is the cycle 2, 3. Now in this permutation, I have a single cycle of length 1 and a single cycle of length 2. Now the others, F2 is the flip across this axis passing through element or vertex 2, and you can actually derive these yourself. And finally F3 is the flip across this axis. So 3 stays put, 1 and 2 become each other, and this is the permutation. The question is, suppose that I have n colors. I'm going to use n colors to color each vertex of this triangle. How many ways are there for me to do this? But suppose that I have a certain configuration with respect to colors, and when I have another configuration which I can obtain by a rotation or a double rotation or one of the flips, I count them as the same configuration. Now, for instance, if you treat all the vertices obviously different, by the product rule, you just make 3 choices. So n choices here, n choices here, n choices here, you get n to power 3. That would be the answer. However, here, let's say this is blue, and let's say this one is orange, and let's say I have another green one. Okay, and let's look at this one. This is blue. Let's say this is orange and green. Now these two configurations, if you treat every vertex different like this scenario, then they are different. But that's an easy question. Just 3 positions, n choices, so the answer is n to power 3. That's not interesting. Rather, if you count these equivalent, because you can obtain one from the other by either flips or rotations. So these are essentially the same triangles. So if this is our approach, if we count these as the same configurations, what are the number of ways I can color this triangle using n colors? Okay, so for instance, if n equals 1, maybe you would like to actually enumerate the small cases to see a pattern, then of course they are the same color for each tree, so the answer is just 1. If n equals 2, then you have 2 colors, so maybe you can color them by all of them by one of the colors, or maybe you can use the other color, or maybe you can use this one in one vertex and the other in 2, and you can use this one in 2, like so. Okay, in n equals 2 case, there are just 4 possible solutions, because if you flip and rotate them, whatever you get will not count as new configurations. When n equals 3, you will have, let's say, all of these the same, or the second color, let's say, or the third color. Or maybe you can select one of the vertices, one color, and the remaining two a different color. So maybe like this. And I also have this one here with the two others. And finally, you can have one where each vertex has a different color. So in total, you have 10. So for n equals 1, it's 1. N equals 2, you get 4. N equals 3, you get 10. Well, it doesn't look like an obvious sequence. You can't really come up with an expression in terms of n on how we are going to express the number of ways to color the vertices.